Okay. Good morning, everyone. Today we will be start with the design of rigid payments. In design of rigid payments, there will be important two factors we are going to study in designing a rigid payments. Out of this, first one is modulus of subgrade reaction. Modulus of subgrade reaction is it is a subgrade support given to the payment construction, or we can call it as the modulus of subgrade reaction from the soil, which is denoted by K. It is K. This can be identified by the formula P upon deflection. Usually deflection we consider, or we take it as 0.125, and P is the total pressure applied on a payment. Here in this Westergaard modulus of subgrade reaction, this subgrade reaction is given by Westergaard. Hence the name is given Westergaard modulus of subgrade reaction. Here, as it is a rigid pavement construction, or we can call it as cement concrete pavement, which can be constructed above the subgrade directly. So here there is no layer by layer construction. Directly on subgrade, compacting a subgrade, over that you will be laying the concrete pavement with the required thickness. Hence the subgrade reaction is very important in terms of constructing rigid pavement. And next, coming to next one is radius of relative stiffness. Radius of relative stiffness means here by this formula you will be calculating the stiffness generated between layers. Stiffness generated between layers, or we can call it as radius of relative stiffness. Usually how we considering a cement concrete pavement of dimension, you can take it as 7-meter width and a length of 45-meter width. If this is a slab, the slab and subgrade, there will be some relation between slab and subgrade. That relation can be calculated by the relative stiffness. If that stiffness is strong, then there is a strong bond between concrete pavement and below, that is subgrade layer. There should be strong bond between concrete layer and subgrade layer. Hence the relative stiffness can be calculated in terms of rigid pavement construction, which is given by the formula L is equal to EH cube upon 12K 1 minus mu square whole raised to 1 by 4. Here L is radius of relative stiffness and E is modulus of elasticity of cement concrete pavement here, not a soil material here, not a aggregate. Here radius of modulus of elasticity of cement concrete, or you can call it as only concrete, which is given in kg per centimeter square. Next, mu is Poisson's ratio for concrete. Usually it will be of 0.15 as per the standard codes. Poisson's ratio for concrete is 0.15. Next, slab thickness. H is the slab thickness. In cement concrete pavement, the H, the thickness of pavement which is to be constructed or provided, is designed. As per the design, the H value, that is slab thickness value, is taken here to calculate relative stiffness. Next, K is subgrade modulus, or modulus of subgrade reaction of lower layer, subgrade layer. Hence, there will be relative stiffness between lower layer and cement concrete layer. This K is given in kg per centimeter cube. It is because kg per centimeter square divided by again per area, that is centimeter. So hence the unit will be kg per centimeter cube. Yes, load by area to the area. Yes, I hope these two equations are understood. That is, one is modulus of subgrade reaction K, and another one is radius of relative stiffness. Now let us see how these two factors or formulas used in calculating subgrade reaction and relative stiffness. Take an example. In this example, compute the radius of relative stiffness of 15 centimeter thick cement concrete slab from the following data. It means you are going to calculate relative stiffness here by taking 15 centimeter thick cement concrete slab. Yes, what are the given data? Modulus of elasticity of cement concrete, that is 2.1 into 10 raised to 5 kg per centimeter square, and Poisson's ratio for concrete is 0.13. It may vary from up to 0.15. Poisson's ratio here it is given 0.13. Modulus of subgrade reaction K value is first condition 3 kg per centimeter cube, second condition 7.5 kg per centimeter cube. Yes. Going to the solution, what are the given things here? Modulus of elasticity, Poisson's ratio, modulus of subgrade reaction. It means by applying directly formula, L is equal to EH cube upon 12K 1 minus mu square, whole to the whole bracket 1 by 4. Okay. Here in this formula, we know E value, that is 2 into 2.1 into 10 raised to 5, or 2,10,000 kg per centimeter square, into H we know, that is thickness of the pavement 15 centimeter. Next 12 into K. What is K? First condition, the K value is 3 kg per centimeter cube. Like that, what is mu value? 0.15. Actually 0.13. Maybe there may be mistake in Poisson's ratio for concrete here given. It must be 0.15. So mu value is 0.15. Substituting all these values, you will be getting 67 centimeter as radius of relative stiffness in terms of centimeter. Okay. Next, going to the second condition, when subgrade reaction is 7.5 kg per centimeter cube, applying the same formula, that is L is equal to 2.1 into 10 raised to 5 into 15 centimeter of thickness, that is H, divided by 12 into K value is 7.5 here, into 1 minus mu square, whole bracket to the raised to 1 by 4, we will get 53.3 centimeter. Yes, this is how the example where we can calculate radius of relative stiffness. The first condition we are getting 67 centimeter, second condition 53.3 centimeter. Okay. Moving to the, what are the stresses? What are the stresses acting in a cement concrete pavement? Stresses in the sense, it is considered as the total load applied, but because of load there will be stress distribution. For example, if it is a concrete concrete slab of 7 meter width and 7 meter length, considering 7 by 7 slab, and what are the stresses applied or induced in it. For example, the load is applied at the center portion, the load is applied at the corner portion, the load is applied at the edge portion. Considering corner, edge and central portion, the total stresses acting on a concrete slab can be calculated. Usually, the stresses are expressed as wheel load stress, temperature stress. Wheel load stress means, as I explained now, the total load applicable on a concrete slab, that is from the vehicle, that is on corner, edge and central portion. And temperature susceptibility, there will be temperature stresses. Because of variation in temperature, it may considered as a stresses and which are applying on a concrete pavement. Hence the wheel load stress and temperature stresses are considered as stresses applied on concrete pavement. Yes, here critical load position. The next concept is critical load position is, as I explained, there will be interior loading, edge loading, corner loading. See here, there are three typical location, namely interior, edge and corner, where differing condition of slab continuity exists. First, interior loading. Interior loading means exactly central portion of the concrete slab, where load is applied in the interior part of the slab surface at any place remote from all the edges. It means the load is considered only central part of the concrete slab, and excluding all other part like corner part, edge part. Whatever the load applying on a central part is considered as interior loading. Next, coming to edge loading. Edge loading, when the load is applied on a edge of the slab, yes, there may be chances of edge failure because of more edge loading. There may be chance of edge failures. Such type of load are considered as edge loading. When load is applied on the edge of the slab at any place remote from the corner, it means considering edge portion loading but not in the corner place. Okay. Next one is corner loading. When the center of load application is located on the bisector corner angle formed by two intersecting edges of the slab, and the loaded area is at the corner touching two corner edges. That's exactly the corner point where transverse direction and longitudinal direction are meeting. Yes, meeting or intersecting. Exactly corner place, the load is applied. Such type of load we consider as corner loading. Yes, hence three type of critical loading we consider here, that is interior loading, edge loading, and corner loading. As while designing a cement concrete pavement, you must be able to consider edge loading, interior loading, and corner loading. By consideration of all these type of loading, the total stress applied by the wheel load can be calculated. Okay. For example, the total interior loading is 1000 kilonewton now. Edge loading, it will be less, 200 kilonewton. Corner loading, 100 kilonewton. Yes, by considering all these three types of loading, the total stresses can be calculated. Okay, so just basic fundamentals you need to be learn this to design a cement concrete pavements. Without knowing this, you cannot design the concrete pavement. Next, moving to equivalent radius of resisting section. As we have discussed earlier, radius of relative stiffness here, the radius of relative stiffness and subgrade reaction, modulus of subgrade reaction. Along with these two terms, this is one more term, that is equivalent radius of resisting section. Considering case of interior loading, when you are considering interior loading, the maximum bending moment occur at the loaded area and acts radially in all directions. If you consider load applying on an interior part, that load is distributed in a circular manner, circular pattern. Yes, and where the load is applying in that location, which is the concrete pavement gives maximum bending moment. Maximum bending moment means there will be deflection will be more at that point, and hence the load is distributed or acts radially in all direction, like circularly it will distribute to the all part of the concrete. That is how much, what is the distance of load distribution, that can be calculated by this formula. B is equal to root of 1.6 a square plus h square minus 0.675 h. With the load concentrated on a small area of the pavement, the question arises as to what sectional area of the pavement is effective in resisting the bending moment. Yes, according to Westergaards, the equivalent radius of resist section is approximated. Yes, as I told now, the load concentrated on smaller area. If it is a pointed load, usually the wheel loads are considered as pointed load because at the point of wheel movement there will be maximum load application. Hence, after load application, the loads are distributed. The loads are distributed in a circular manner, and that area can be calculated by using this formula. Yes, from this formula, what is B? The B is equivalent radius of resisting section. After that, he has given one condition. The B is measured in centimeter when A is less than 1.724 H. What is A? You must know what is A. Radius of wheel load distribution. What is the radius of wheel load distribution? That is small a, and H is slab thickness. Here, as per this condition, A is less than 1.724 H. You consider if A by H is equal to 1.724. A by H, see, you can read at the bottom here. When A is greater than 1.724 H, it means A divided by H value, that is radius of V load distribution divided by slab thickness value, is greater than 1.724, the value of B will be same as radius of V load. If A by H value is less than 1.724, then you need to calculate B by using this formula. Okay, now I will repeat it again. When A is, or A by H value is greater than 1.724. Suppose A by H, radius of V load divided by slab thickness, if you are getting 1.8, then the B value, whatever you are calculating here, radius of resisting section, B value will be same as radius of V load. If A by H value is less than 1.724, suppose if it is 1.6, then B value should be calculated by using this formula, by considering slab thickness, by considering radius of V load. Okay, this is the condition to calculate radius of resisting section. Okay, by this formula, let us see one example. Only this much you see. Let us see an example to calculate B value here. Compute the equivalent radius of resisting section of 20 centimeter slab, given that radius of contact area V load is 15 centimeter. It means what he has given, slab thickness is given, that is 20 centimeter, and radius of contact area, that is 15 centimeter. H and A are given already. So what your work is to check the condition. A by H 15 by 20 centimeter, you are getting 0.75. Check it. The 0.75 is less than 1.724. Hence, you need to use the formula. If it is getting more than 1.724, then B will be same as A, that is 15 centimeter. But here the condition case is you are getting less than 1.724. Hence, applying the formula, B is equal to root of 1.6 A square plus H square minus 0.675 H. Just substitute the A value, H value, you will get 14.04 centimeter. Yes, that is 14.07 centimeter is equivalent radius of resisting section. Actually, if it is greater, we would have taken A value as 15. But to get the accurate value, see, exact value is 14.07 centimeter. But as per this, you may take 15 centimeter. But going with the accurate value, calculating by formula, we are getting 14.07 centimeter as radius of resisting section. It means up to 14 centimeter from the application of load up to 14 centimeter radial distance, the resisting section, the load resisting section is considered. Okay, are you clear with this? Next, now as earlier part, we have discussed the stress acting on a rigid pavement, that is wheel load stress and temperature stress. Wheel load stress, here as per the early study, that is Goldbeck, the 80 Goldbeck indicated that many concrete slabs failed at the corner point. Corner point, usually the concrete pavements are failing because of because of load application at the corner point. The corner point has low resisting capacity. He derived a corner load formula that is given by him. SC is equal to 3P upon H square. Usually, that is SC is stress due to corner load. Because of corner load, the pavement will get rusticate. Yes, to avoid that, he has given the formula. SC is stress due to corner load kg per centimeter square, and P is the corner load assumed as a concentrated point load, and H is the thickness of slab. By knowing this, I can calculate what is that stress applying at the corner point. Okay, this is small formula. You may use it in a further problems. Next, Here comes the important part of the concrete pavement, entire concrete pavement. That is interior loading, edge loading, corner loading, the equations given by the Westergaard. It is a very, very important equations given by the Westergaard. By using these equations, we can calculate the stress applying at a interior load, stress at edge load, stress at corner load. Here you just imagine a slab. Imagine a slab. In that slab, interior loading application, edge loading application, corner loading application. You just imagine where is the point of load application. Here, Westergaard he has given three equations. That is SI, SE, SC. SI indicates stress at interior loading, stress at edge loading, stress at corner loading. Here, interior loading SI is equal to 0.316 P upon H square, 4 log to the base 10 L by B plus 1.069. In this equation, P is the total wheel load applicable, wheel load application in terms of kg, total wheel load, and H is the slab thickness. Yes, by knowing slab thickness. Next, here comes L and B. These L and B are nothing but radius of relative stiffness, as we discussed earlier, that is L, and B is this one, radius of resisting section. Yes, these two are considered here in this equation, radius of relative stiffness and radius of resisting section. Okay, L is relative stiffness, B is resisting section. This you must be remember. Hence, the equation is proved here. SI is equal to 0.316 P upon H square, 4 log L upon B plus 1.069. By knowing L and B, by knowing slab thickness, by knowing total wheel load, the total stress at interior load can be calculated. Similarly, edge loading, SE is equal to 0.572 P divided by H square, 4 log L upon B, 0.359. Yes, only these constants values are changing here. In these two equations, constants value are changing. Because hence, since it is a empirical formula, there will be change of constant values. Next, corner loading. Corner loading 3 is a constant value, P upon H square, bracket 1 minus a root 2 divided by L, bracket complete. Here actually there should be raised to 1 by 2 or 0.5. Some printing mistake is there. You can note down that 3p upon s square, bracket 1 minus bracket a root 2 upon L, bracket complete, raised to 0.5, whole bracket complete. Okay. Yes, by this expression, SI, SC, SCR, maximum stress at interior, edge load and corner loading in terms of kg per centimeter square. And H is slab thickness in centimeter, P is wheel load, and A is radius of wheel load distribution. In third equation, A is there, radius of wheel load distribution. And L is radius of relative stiffness, and B is the radius of resisting section. Yes, you note down these three equations. Based on three equations, you will be solving many problems on this.
Yes, sir.
Okay. Okay, we'll move next one. Yes. See, as per the IRC guidelines, this is Westergaard has given very earlier. He has given the equations, and based on the equation, substituting the value, then only we'll get the stress equation. Then only we'll get the stress equation. Now, as per the IRC guidelines, this is the IRC guidelines. IRC has given some figures or charts, we can call it as. From the chart, directly we can calculate stresses. For example, see edge loading. Edge load stress is given a chart. X-axis is slab thickness, y-axis is edge load stress, and these lines are K value. K is nothing but subgrade reaction value, modulus of subgrade reaction value. Here, by knowing K value, we can calculate edge load stress directly. Yes, as we all know slab thickness, by knowing the slab thickness, by knowing the K value, that is subgrade reaction value, we can calculate edge load stress directly, which is given by the IRC. Similarly, see the corner load stress. Here slab thickness is there. Here also K value is there. Directly we can calculate corner load. It means by knowing slab thickness and by knowing the K value, subgrade reaction value, which can be calculated by conducting experiments, plate load test, or any soil experiments. By conducting experiments, we can calculate corner load stress directly. Okay, we just go on referring this table. Also, in this graph, he has given the wheel load A value and modulus of elasticity value. Here P is total wheel load, A is radius of contact, and E is modulus of subgrade reaction. By usually considering a standard value in the sense on an average of wheel load 5100 kg, on an average of radius of contact 15 centimeter, on an average of modulus of elasticity E value, and Poisson's ratio 0.15, this graph is designed. The IRC is designed based on the average value of all these standard terms. Okay, based on this, the standard graph is designed. Based on this graph, we can analyze and we can calculate the stresses. Okay. Okay. As with this concept, we can solve a next numericals.